let's present slides. Here we go. Morning. Hope you had a good break. I did. Break from some things, got other work done. And anyway, Nick sent me pictures of his cats. They look about as lazy as mine. Anyway, so let's get started. A few reminders. We have a test coming up on Friday. It's on chapters 5 and 6. I've got a draft test ready at the moment, but going back to making some revisions to it. That test 2 was quite a disappointment to you and to me, and as I said, I think part of it, at least the issues, were setting expectations, and it's doing multiple choice testing is not my normal routine. That I would have had tests like you would have seen in Quant 1 previously. And with math tests, it's really easy to design a test to set, and have expectations at the outset of what would be a 90%, what would be a 70%, what would be a 50%, and design a test accordingly to meet those sorts of expectations. I'm finding that very difficult to do in a multiple choice environment. It's not like there's part marks, and you can understand the nuances of what students have done and that sort of thing, and adjust things in the grading as well as the question design and so on. That's much harder to do in a multiple choice one, and that the getting a near perfect score in a multiple choice is actually very, very difficult to do, because it's easy to make just a little mistake, a slight difference in interpretation of a question. And then regular problems, even in your assignment ones, I can see when students interpret something somewhat differently than what I intended, but it's a reasonable interpretation. You can't see that in a multiple choice. It's black and white, and so many things are not black and white. They're different shades of gray, and so it's I'm having to adjust things accordingly, and I think I'm on the right track at the moment, and we'll try to do a much better job for you with this test number 3. So, getting ourselves started here. The break weather was cold, but we had some all the lakes around, all across the province are all frozen now, and most of them froze when the weather was reasonably cooperative, so that the ice surface isn't that bad. This is Frog Pond. That's not far from where I live, and it's the ice was fairly smooth. There were lots of patches that were very glassy, and the day I was out there with Dora, there were probably 100 people, young and old, skating all over the place. Some little hockey games going on in different corners, and others just skating around. And it was quite nice to see. But we're seeing that in ponds everywhere, and it's quite nice. So many winters we don't get any good skating days. I'm not a skater myself. I never skate. Hate it. But I do enjoy seeing other people enjoying it. But now we're back to work and try to remember where we left off or what we have to do next. Breaks are nice, but they're hard to get started again afterwards. Um, we we had several intense classes on pivot tables, and that was your last assignment. Beat you up on that, and then it sort of lightened up with a little bit of theory, in a sense, on different things. And so now we're trying to transition from exploring our data to actually building models based upon the data, that we've got some understanding of what we've got. And models are a way of creating what I'd call actionable knowledge, that not only do you have some basic understanding, but it's giving you insight as to direction. In particular, we're going to look at models that help us make predictions, so that if we do this, this is going to happen. So we can make a decision. What would be, if we want a certain outcome, what should we do to achieve that? Or we can at least play it with what if type sorts of things. In Quant 1, you looked at what are called prescriptive models, that they told you, once you built the model and you put it into solver and that type of thing and got an answer out, it said, fine, if you want to maximize profit, do the following activities. So it was telling you exactly what to do. These models that we're going to be looking at are generally going to be predictive ones, where it's saying, if we do this, this is what will happen. With this customer, this is the risks you're taking. This is the type of customer there. Do you like them or not like them? And you've already probably set up criteria for who do you want and who don't you want on your team. So uh, they're still very, very useful models. When you did break-even analysis, break-even is an example of a descriptive model where it tells you what if. It is, in a sense, a predictive model. If you make 100 units, your total cost is going to be $7,000. It says consequences of certain actions, and that's what we're getting into now. But we're going to build them in break-even. You were given all the numbers and terms and then linear programming. This is one where we have to build the model and we aren't given the numbers to put into it. We have to invent the appropriate numbers. So the example we're going to run through, we already started looking at, and now we're going to start building that model with um, building formulas around it and try to get better formulas. And the data set we're using has to do with credit card balances and characteristics of the customer. So how do we predict their credit card balance given the customer characteristics? And we want to build the model that'll give us the best predictions. And we define best as being ones with small errors. We know that our predictions are not going to be perfect. We're going to be too high with some customers and too low with others. But we would like those errors to be small as possible. We can accept little errors. They're not a big deal, but we really don't want large errors. And so we're going to add an extra penalty onto big errors. We're going to take the size of the error and square it. So a small number when squared is still small. A big number when squared becomes huge. So if the error was 10, it becomes a penalty of 100. If the error is 100, the penalty is 10,000. So it expands by a large amount. And so we're going to find the minimum mean squared error, prediction error, which led to some fancy math, which is nice behind the scenes. We're going to do it all in Excel. And so you don't have to worry about the complexity of the mathematics and that sort of thing. So whether it uses nice math or not nice math may not matter to you. There are still other benefits to using this squared error that it's getting to the point now with our computational computer capacity. We can have very inefficient methods on big problems and still we can manage it. In the past, uh, we needed super efficient methods to be able to get answers relatively quickly. I can think of doing analyses in the early days of desktop computers, and for a little tiny problem, I would set up the problem on my computer and I would come back in a day or two to see if it gave me the answer yet. I ended up having to buy a second computer so that I could do my day-to-day work on one and the other one to do these computations that, as I said, would take days at a time to be able to. Um, Today it's done super quick, but our demands on computers keep increasing. So we still want things that are relatively efficient. We're going to be using regression analysis in Excel. And Excel is going to fit the model. It's going to determine the coefficients. So if you could imagine a break-even problem, building a cost function, instead of being given a fixed cost and a unit variable cost, that so that it had nice numbers, we could just put them in and build a simple formula. What if what you had was historical data for the last month, and each day how many units you made and what the total costs were incurred for that day? And so you had a whole bunch of points. And from that, you were then asked to work out, well, what is the fixed cost, the setup and overhead for the day? And how much is the unit cost for each day? That's the type of environment we're getting into. We need to find what are the fixed cost and unit variable cost that would fit into a formula. It isn't given to you like you might have had previously. We'll also try to emphasize when you're building these things how to interpret the coefficients in the model. Now, in a cost function, most students find it's relatively straightforward to start interpreting those coefficients, understanding what a fixed cost is, what a unit cost is. The models we'll be using are going to be simple straight line formulas again, but I want to make sure I can interpret those coefficients appropriately. And that what does the slope mean? What does the intercept mean? And I'll be hammering away on that it is really important. It's the basis of causal analysis, understanding what's the impact of changing a variable and on your outcome. That we're going to look at model performance in two ways. One is if it was a cost function and I was estimating fixed cost or variable cost, anything I get is going to be an estimate. It's just based upon the data I've got. So how accurate are the estimates? So that's one aspect of accuracy I'm going to look at. The other is making predictions about, okay, here's a job I'm producing. How much is it going to cost me to produce that job? That I'm making an estimate, maybe to give a quote to a customer, but the actual cost is going to be higher or lower. So how accurate is that prediction going to be? And we're going to use two measures of measuring accuracy. That a term called R squared is the most popular measure of doing that, but I'm going to emphasize standard error, which for me helps me understand better what I mean by accuracy. But we'll get to that. So that's basically what we're going to go through today for a very simple model. So last day said a model, and we're looking at a model as a formula. There are other types of models. They don't have to all be mathematical formulas, but we're going to have one that relates the customer characteristics, some function. You put the numbers in there for the customer characteristics, and out comes the balance. And in quant one, you would have seen like a cost function, or you may have seen more complicated ones like in finance, the figuring out loan payments. You had to put in various characteristics of the loan, how much you're borrowing, how many months, what the interest rate is, how payments are made, those sorts of things. And from that, it'll tell you, okay, what your biweekly car payment has to be. That so some formulas can be complex, some can be very simple. We're building one from scratch with just using data. We don't have theory. So we're going to use a strategy of keeping it simple, and that we're going to work with the simplest model and then start incrementally adding complexity, but we'll only make it more complex if we think we're getting an improvement in the performance. If we find it's not helping us, then we're going to go back to what we had before. So we're always going to try to keep our models as simple as possible. This is, there is in many instances a desire to add features, add complexity right at the start. I find that not a very good design principle. that you have to identify what's most important to you, do that right, then add the other features, that type of thing. And as a design principle for designing products, designing services, building something, it helps keep you focused on what you think is most important. And it generally comes up with a design that's more robust, that it's not going to easily fall down, that if it gets hit by something, it's not going to. Complexity makes things more fragile in many cases. So try to keep away from it. I know our cars today are have an awful lot of features to them, but you can't get them serviced anymore. You can't just do it yourself any longer because of all the computer technology. That complexity has made it more difficult to do any repair work or servicing on a vehicle. But at the same time, they may be better, but you'll have to weigh the balances. Is that complexity adding value? It does appear to be, and that's why we've gone that path. But you've got to make those types of evaluations. So if I'm looking at math, what's the simplest formula I can get? It's a straight line. A straight line is y equals mx plus b. It's an intercept and a slope. There's nothing more to it than that, like a fixed cost plus a unit cost times the number of units. That we have a target variable or a dependent variable, that's y, that's our credit card balance. And then we've got to choose what variable to use to make the predictions. If I'm only going to pick one, I'm going to pick what I think is the best one, and it's a straight line. So I'm going to look at linear correlation, and the one with the highest linear correlation was credit rating. So I'm going to build a formula that has some intercept plus slope times credit rating, and I'm going to do it in Excel. Okay. Now I'm going to jump into Excel, and I'm going to show you how to do this, and I'm going to show you the cheater's way of doing it for simple problems, and then but I'm going to show you the method we're going to use, which is more flexible because we can get into a lot more complex problems. So this is the data set I'm working with. And if I'm building models, I'd suggest each time you go to build a model, grab the data that you want for the model and put everything there in a package. Okay, so leave the original data set. And sometimes we can just get the output and leave the data. I like to keep it all together. So I'm going to go and take rating. I'm going to take balance. I'm going to copy them. And I've got a new sheet here, and I'm going to paste it in. Make it bigger so I can see it. Okay. And so I've got the rating, that's my X variable, and I got balance, that's my Y variable. I tend to like to have my X variables on the left, Y variables on the right, in part because when I create charts, I want the axes to be the right way around. I talked about this before. If I take these two guys and I am just going to insert a scatter chart like we had last time, and by having rating on the left, it ensures that my rating becomes the horizontal axis and balance gets on the vertical axis. Okay? And I'm going to put a straight line through all of this. That um, I think I may have shown you before, a straight line that fit through. If I'm in design in a scatter chart, go up to quick layout. This is the cheater's approach. And there are a whole bunch of different layouts. And it generally has to do with what's put on the different axes and how I configure it. But there's some that have, here's one that has a line that gets in it. And there's another one down here. It's the 9th one on this list. And I gotta use this guy. I'm gonna take out this is junk. Okay, gives me more space. And so down here, it was the rating. And over here is the balance on the vertical axis. And if you were on the class last time, told you I don't like reading uphill. So I'm going to go over here and I'm going to rotate this. You don't have to do this. This is just my preference. Okay? So I like it this way. It's easier for me to read. And there are two things that are here. One is the equation of the line, and I'm going to change that because I can't see it. Not very well. Let me make the weight bigger. And I'm actually going to do something else. I'm going to put a line on top of it. Oops, excuse me. Hold on here. I just want to see that point now. I'm going to connect from here. See, their lines aren't long enough for me. I want a really long one. And I'm going to now color it in, make it thicker. Okay, so this is the line, and this is the best line through the scatter. We're going to calculate that in a moment. By picking this layout, Excel has also given me an equation. It says the equation of the line has an intercept of minus 390.85. Let me color that in. I'm going to put it in blue. And it has a slope. So this is, I should probably make a note of this guy. Don't forget it, it's bold. And I'm going to color it blue too. So a few things here with this line. It's a straight line. A straight line has an intercept. That's the value of y, the vertical value, when x is equal to 0. In a cost function, this is fixed cost. It's the cost when you're not making anything. And this is telling me this crosses at minus 390. That's this spot here, down below 0, minus 390. We'll talk about that shortly. And it says the slope of the line, that's like the unit cost in a cost function, the rate at which this is going up is 2.566. So Excel will give this to me, boom, really quick, nice and easy. And it gives me this other thing here called R squared. And we'll talk about that towards the end of the class, which is a measure of how good a model this is. But wait till later, we'll get to that. I should note that in my data that I've got here, if you look through it, there are some zeros here, but there are no blanks, not a single blank all the way down, okay? And if you're doing a scatter chart, you can get a scatter chart even if you've got blanks. So if I took this guy out, okay, it will probably take that point out of this picture somewhere, but it won't change any of the numbers, okay, that I can still, well, it still will allow me to calculate the line that goes through the scatter. So with blanks, they end up just being ignored because I can't plot a blank. That this one here, it's 138 on the vertical, but, or sorry, on the horizontal, but on the vertical axis, I don't know where to put it if this is blank. It isn't automatically 0. Um, so let me see if I can take out one that you can see. I don't know if you can see the 1400. Oop, did you see that guy disappear? I don't know. See him reappear? He's sitting up around here. Let me just make him come back again. Yeah, he was sitting right up around there. That if you take a value out, a blank out, it just disappears from the picture. And it turns out Excel can still go and calculate this line. The method I'm going to use in a minute is it's actually the same method behind the scenes, but it will crash. It won't work if I've got any blanks. So if you took your data that you used for assignments 1 and 2, and I think in it we've got high school average and grade point average. And you might think that if a student had a higher high school average, they'll have a higher grade point average. And you can do a scatter chart of GPA versus high school average. And you're going to find it's a big, messy scatter, but you can do it. And there are a bunch of blanks in your data set. And you should also be able to get it to go and do this type of thing of calculating a regression line for you. That what Excel has done is basically hidden all of those, removed those records before it did any work. For the method we're going to use in a minute, you won't be able to do that unless you take those two columns, filter out all of the blanks. So just, hide those records, those rows in it, then copy them after you've filtered out all the blanks into a new sheet, and then do your calculations. Because to do what we're going to use, blanks are a problem. Just a warning. Students have tried to do that before. How did I extend the line? I cheated because it won't let me extend the line. What I did was the line that was there already, I was into format, and I used a drawing tool. I took a straight line drawing tool. I clicked on the top spot up here, and I drew a line that sat on top of the other line. The old line is actually still there. It's behind the scenes. I put this one on top of it. But Excel won't let me extend the line that was automatically drawn. So I've drawn my own line on top. If I change my picture, see, there it is. So this is my new line, this guy here. This is the original one. So if I go back and put it this way, I've got to now go and move this guy so it lies on top properly. Hide the proper line. I haven't found a way to get it to do it and fix it in that sort of fashion. Okay, let's get back to what we're supposed to be doing here. So I'm going to use a thing yeah, there is a thing in terms of trend line that, okay, forecast will extend it. Be cautious about that. Let me try to remind me to talk about that later, because trend lines are a very dangerous thing to use. They're good in certain cases, but they're dangerous. Particularly for this type of data. And the so in my slides, I'm saying I'm going to bring up regression. Let me go back and I'm going to actually do that. So what I'm going to do is go over here to data. I'm going to go to data analysis. And among the different tools is one called regression. That this name goes back to probably the first published application of the tool that's used, the mathematics, back in the 1800s, I think. And it had to do with an application of heights of fathers and their sons. And in the title of the article, it talked about regression as regressing, of going backwards. And that name is stuck, and it now describes the actual technique. So the to use this, I need to be able to describe what's on the vertical axis. What's my y variable, which is balance. So it starts out, what's the y range, the y variable. So that's balance, and it's in column B, and it goes from B1 up to B401. That's the last row that's there. So you could go and just select it, or you could type it in. And the x range is the x variable. It goes, it's in column A, the rating, and it's in column A, starting at row 1 with the label, and it goes all the way down to row 401. I'm including my labels, and I would recommend including labels when we're doing regression. that it makes the output easier to read a little bit. That the output, the standard, the default is to put it into a completely new sheet. For this example, want to keep everything in one place for us. So I'm going to put it in this one, and I'm looking at putting it probably in D, and my first blank space is 16. So I'll put it down here. I'm not going to check any of the other boxes. And some of them I recommend you don't ever check. Don't bother with constant is 0. Even if you wanted your line to go through the 0, like a revenue function that goes through 0, 0, uh, there are a whole bunch of issues associated with doing that type of thing that unless you really know what you're doing and you have some really good knowledge of regression, stay away from it. We also don't want to deal with confidence levels. We are going to look at down here at what's called residuals. I'll bring that up next class. And we're not going to get into probability stuff that doesn't belong in this course. But it is applicable in other settings. Okay, so let's just keep it simple. I click OK, and I get my results. And it's reasonably quick. It's not a big data set, so the response time is quite good. And that if a bigger data set, you might actually have to wait a little while before you get an answer. The table has some descriptors in it and then a lot of numbers. I'm just going to widen columns so that the descriptors are better. And this actually screws up my picture up here. So I'm going to fix that back up again. Whoops. There we go. All right. So the output you get is in 3 boxes. One is called Regression Statistics. Another is called ANOVA. It's shorthand for Analysis of Variance. We don't need to get into that. And the third one is going to tell us about the model. And that table goes way across. We don't need all this stuff. This is generic output. So you're trying to give the user everything they could possibly ask for. And most of the time, you don't need very much of it. And we don't need an awful lot of it. That we'll focus on what's really important to us. So this is how to do it. And this is what comes out. So this is a table I just had. And I just want to highlight certain parts of it. The first block I view as being model performance information. So is the model really good? Is it going to meet our objectives? And we'll discuss that a little bit later this morning. But that's sort of my first thought as to performance. And that's often the first question you ask. Well, good. Is this model any good? No, it isn't. Okay, let's go back, try something else. Or if it is, okay, what does it look like? But it's often the very first question. It's like you getting a test back and saying, well, how did I do on the test? And then seeing, well, what did you get right and what did you get wrong? So this is the first question that comes to mind. Second table is one that if this was a stats course, that we would probably pay some attention to. But even that, I'm beginning to think is antiquated in the sense that um, uh, years ago we did all this stuff by hand. It was really painful. Or we had a computer that would do some stuff and other stuff we'd have to do by hand. And this was a table that helped summarize a lot of our calculations, and it reflected certain aspects of the theory. And it was a really good aid for us in doing some statistical analyses. But today we probably don't need it anymore. But it's a legacy thing that it's probably going to be another 20 or 30 years before people start using it like they used to. You don't need to worry about it, but unfortunately you will have to see this in a statistics course. And the last table tells us actually about that formula, that what is the formula of the line that goes through. And so this is very useful to us. But the clutter to the right is again getting into the statistics that definitely at the moment we don't need. And what I just need the stuff that I bolded here. That's the really important stuff for me, and what we'll be working with the most. That so if I'm looking at these numbers, pay attention to this one here. That or let me go to the Excel stuff version. If I go down and I look at this number, okay, and I think I put it in blue before. I'll put it in blue again, and I'll make it bold so you can see it better. And this one I had in red. Oops, hold it. And you may notice those two numbers are the same ones that I had up here at the top. They're my regression formula. So I'm going to go and write out my formula here. My formula now with words and the like, instead of just the X's and Y's, are the words I'm using are important. I'm predicting balance, but I'm actually predicting the estimated average balance. Both words are important. It's going to be equal to minus $390, $90.85. Oops, 300. Yeah, excuse me. And for that, I'm going to add $2.57 times the rating. Okay. Move over a little bit so you can see all of this formula. So what's it telling me here? That the this is going back to my picture. Okay. It says that if I have a customer whose balance or whose rating is 0. Now you look at these ratings, they go from about 100 to about 1,000. I don't have anybody with a rating of 0. But if I did, down here at the bottom, that person's balance, I estimate, be minus 390. Negative. What's it mean to have a negative balance? What would it mean if your credit card balance was minus $390? Any thoughts? Type it in chat. You have a debt? You owe the bank? That's your first thought because it's negative. If it was your bank balance, yes. No, it's they owe you. This is how much you owe. So this is 500 means you owe 500. If you owe minus $390, it means they owe you. That I can think of a occasion where I paid off my credit card balance, but then I ended up returning the product back to Amazon again, and I got a credit back. I didn't buy anything that month. So my next statement said I had a credit of $250. My balance was minus 250. It means they owed me money that I could spend up to $250 before I had to start paying them for it. So this is sort of silly to have to estimate, who has credits on their account. It's just, if you had a credit rating of 0, who gets a credit rating of 0? Probably someone that has filed for bankruptcy multiple times, doesn't have a job. Um, they're just, nobody would want to give them a credit card. These are people that even cash money won't give them payday loans for. That no, none of these people have cards right now. It's a number. That's all it is. I've drawn a straight line here that I really want the straight line for out here, but I need an equation, and the equation of the line needs an intercept. and that ends up being minus 390. There are an awful lot of cases where the intercept in a regression model is a meaningless number. It's nothing. Don't be cautious reading any interpretation into the intercept. Okay? The second thing goes back to, whose comment was it? Yes, Dominic, about trend lines. So if I extend, this is what I've seen of customers. I've seen customers with credit ratings generally between 200 and maybe 700, and a few people below that and a few people above that. But the bulk of them are between 200 and 700. I know these customers well. Customers that are between 100 and 200 or between 700 and 1,000, I know some of them, but I don't know them really well. So ones I know well, I should be able to describe well. Those that I don't know well, that's trickier in terms of making a description because I don't know them that well. With trend lines, you're extending out beyond what you've even seen before. So extending my line down here, I've never been there before. And so I don't know what's going to happen. Or if I could have ratings above 1,000, if I extend it out here, I've never seen that before. I don't know what happens. That, and we'll see, if you look at this, and this is something we'll take up the next week, actually. If I look at this, some might say it looks like an S. It looks like flat, goes up, and then it slows down, and maybe it even flattens out. So maybe this is a wiggly curve, but over the section I've looked at it, it looks like a straight line. So it's generally recommended you don't extend your line or try to make predictions outside of what you've seen before. Be very cautious on that. That try to restrict your attention to your current experience. Trend lines that Dominic talked of is generally applied with time series data. And that's a topic that I chose not to include in the course, but I'm thinking in future we probably should look at time series data. That not that the techniques are really that different that we'd use for it, but there it's the data is over. This is a time axis here. So if I had a graph of COVID data and I looked at the number of COVID cases per day or something, and there they keep talking of waves because we've come up through a wave, and at the moment it looks like at most countries in the world we've peaked and we're now starting to come down again. But then there's the question, there are two questions actually. Will that line go down now rapidly? It's going down because we're all wearing masks, we're all distancing, that in places like Ontario and elsewhere, they've had very severe lockdowns for a long period of time, and those are finally starting to have effect. And so now we've pressed and are coming down because of those preventative actions that have been taken. We're probably also hitting just the very beginning of the benefits of vaccination. And over the next several months, we may see that line go down more steeply because of vaccinations. But as Newfoundland is showing us, there are variants to the virus that are spreading very, very, very rapidly. And Newfoundland, that had been sitting at around zero, has suddenly shot up. And it's all of this new variants, all their new cases are the new variants that are highly, highly infectious. And so we have at the moment combination of three factors happening. One is lockdowns and restrictive practices, and that's, we could extend the trend line if we kept those in place. But now Ontario's opening up and other places are opening up, so that's changed. We've got the vaccinations, which is a big plus, is going in, and we've got variants, which is a really negative thing. So a combination of three things happening, And so if this was the situation you were in, say this was our COVID cases and they're coming up and we were starting to flatten the curve, we're asking what's going to happen next. I can't extend the trend line because actually the past is no longer relevant. All of this data was before we had the new variants, before we had vaccines, and before we started opening up again after a lockdown. And so the past isn't a good predictor of the future. Trend lines are good when the past is a very good predictor and we're in a very stable environment. But if your environment has changed, the past may no longer tell you anything about the future. It's time series analysis is interesting because it is really driven on your understanding of what went on in the past and what aspects of the past can you expect to carry into the future and what aspects may not. Anyway, so back to what I was looking at here. These coefficients, this was the intercept, and the 2.57 is how quickly this line is going up. What's the steepness of that line? And it's like a unit cost type of thing. I'm probably getting off track here. So I just explained about the intercept, and so that's what I'm saying. Down here is sort of meaningless. Don't read too much into it. The slope is how much a 1 point change in rating might matter. So 1 point change is sort of small. If I had two groups of customers, one of them that had a credit rating of around 500, another group around 600, so they differ by about 100 points, I would expect their balances to differ by about $257, 100 times 2.57. But I've got to remember this has to do with an estimate and an estimate of the average. And that's why my line said estimated average balance. Look at this line going up, okay? And here is a rating of 500, estimated balance around $292, $293, thereabouts. Okay? It's where the orange line goes. So individuals are above that line and they're below that line. This is just the average. The line is the average of those customers. So among customers with a credit rating of 500, their average balance is around $200 or $892. So this is just the average of people above and below that line. And up here, the orange would be the average for people with, say, a rating of 800. It'd be above and below. And here, average of those with a rating of, say, 200. And in some spots, I've got, lots of data I can actually look at and see, is it a good line? In other places, maybe I don't. Down in the middle, I've got lots of data. I can see that. But at the ends, I can't. But the line is still trying to describe, on average, what should they look like. But it's only an estimate. Okay. Oh, we'll get to it. Is it a good average? I've chopped off my slide here, but there are about 21 customers I found with a rating between 480 and 520. And I looked up their balances and I averaged them. And it was 893. Yeah, I couldn't ask for better. I'm really good at estimating the average. But their actual balances went from $250 to $1,411. So I'm not very good at estimating actual balances for actual customers. My line is really good for estimating the average, but not for individuals. So what are you trying to predict? Are you trying to predict what the average customer will do or what an individual customer will do? And a model may be really, really good at one and not very good at the other. Well, if it's not good at the average, it's not going to be good at the individual, but it can be great at the average, but not for the individual. The table also has standard errors in it, and those are useful because these are my line, my average is only an estimate. So the estimate could be wrong. Maybe the intercept isn't minus 390. Maybe it's a bit larger, a bit smaller. How much larger? How much smaller? And the slope I've got is 2.57. It's an estimate. Maybe it's larger or smaller. How much larger, smaller? What would be the effect of a change? So that's where empirical rule. I know empirical rule doesn't always work. It didn't work on your assignment too, because your data was highly skewed. But generally with estimates, my data is not skewed. There is some balancing left above, below to it. And so with the slope, it might be a little bit higher, a little bit lower. Maybe it's not 2.566. Could be off by 0.075 either way. And that normally we would say that don't be surprised if you're off by one standard error, but you should not be off by more than two. That's my general rule of thumb. So my estimate could well be off by 0.07, 0.08, 0.1, but it's probably not going to be off by more than 0.15, 2 times that standard error. So maybe the slope is as low as 2.42, maybe as high as 2.72, but I don't think it's any more than that. And the same type of thing happens with the intercept. So if I looked at my intercept, maybe it's not 390. Maybe it's off by a little bit either way. And if I look at two standard errors, that could be down to 342, minus 342, or maybe minus 448. Oops, minus 3. That So I've got these two blue lines here. That's where it could wiggle. So maybe I could shove my line up or down by a little bit. That's moving my intercept up and down a little bit. You see, it doesn't seem to move that much. There's a lot of scatter here. And if I moved the slope, it's like wiggling the slope. So it could move a little bit, but it's not moving a huge amount. So I'm not going to have widely different predictions probably with that average. So predicting average balance for a group of customers, for all customers with a balance of, or a rating of 800, or all customers with a rating of 300, I can probably do reasonably well for the average, but maybe not for individuals. Most people evaluate quality of the model not in terms of predicting averages, but trying to predict individual values. And that is hard. Predicting individual behavior is very difficult to do. Predicting average behavior is often, we can do it in a lot of cases. We just have trouble when we get down to the individual level. So there you've got to think about consequences. It's not, when saying things are accurate, that does it matter if your prediction is off by $100, if there's an error of 100 or 200 or 500? That you've got to think about, well, what are the consequences? So if I made a prediction and I was off by $300 instead of $100, what would be the effect of that? What would happen? What would I do? Would I do anything different? What are there consequences to it? And this is critically important. When at the very beginning of the course said that we start with business understanding. And what's your business problem? Oh, I'd like to predict credit card balances. Okay. So what would success look like? Well, I'd like to predict them very accurately. Okay. But what is success? What is accurate? What are your expectations? That, well, I'd like them to be accurate. I think that's self-explanatory, isn't it? No, because we're going to make mistakes. If I could predict it within $100, so I predicted someone's balance would be between $800 and $1,000, is that good enough for you? Okay, maybe. Yeah, that sounds good. Well, suppose I couldn't do it that well. Suppose my prediction was between $600 and $1,200. What do you think then? Oh, I don't like that. I don't think that's very good at all. Okay, why? Those are just numbers. Um, how would you treat the customer differently if their balance was 600 and you thought it was 900? How would you treat the customer differently if their balance was 1200 and you thought it was 900? Think through those things. And if they don't have an answer for you, then tell them to go back and figure out what your problem is. Because if they don't understand what an accurate forecast is, they don't understand how they're going to use that information and how the error in that forecast for that customer is going to affect their business enterprise. It's probably actually that they don't care about individuals. They're interested in doing it on average because they've got 1 million credit card customers. So they're not looking at individual ones, they're looking at the customers with a credit rating of 500. What do they borrow on average? There's a lot of question and answer back and forth, and you may need to, at this stage, go back and revisit that, or before you get too far into your model, you want to know when to stop. When have you got something that's good enough for the customer? Don't give them a luxury model sedan when really um, they're better off just taking the bus. What are their real needs here? Because this could be very expensive to build a more accurate model, or you may be setting yourself up for disappointment because you could never achieve what they are asking for. Their expectations are totally unrealistic, and this is not uncommon. Very often, they haven't thought through the issue, haven't thought through the problem. But we need that to be able to evaluate whether or not we've been successful in this project, because they need to define what does success look like. So there are two ways of doing this. The one that I like, because it puts it in this tangible fashion, like how accurate do you need it, is to look at the standard error of the model as a whole. And the table there says that the standard error is 232. What this means is if I'm making predictions of individual customer balances, do not be surprised if my prediction is off by $232. And it's possible it's going to be off by twice that amount, but that won't happen very often. Okay, it's again empirical rule that the it, don't be surprised if you're off by $232, but it's unlikely. It's possible, but it's unlikely you're going to be off by more than $464. When you think about the 464, is that a big number? Well, most of those customers had balances between $0 and $1,500. The average is a little more than $500. So, um, it's like a spread of 700 or 800 above or below forecast is probably as bad as it's going to get. And you're telling me that the best you can do is to be off by $400 or $500. Look at that scatter chart again. Look how wide it is. So my predictions are not precise. We already saw that, but this puts it in a more formal fashion that it's likely for that customer with a balance of 500 or a rating of 500 that their balance is somewhere between $400 and $1,400, somewhere in that neighborhood. You could be off by quite a bit. Don't be surprised. Okay. If that's not going to be satisfactory to you, then you need a better model. And that's what we're going to do in the next two classes, how to build a better model. Because this one is the simplest one. This is the base model. And now we're going to look at the, one level up. And then we're going to look at the super deluxe model beyond that. But you're going to pay more for it. just like with your car or any other product. So that's one way of looking at it. But it's amazing how many people look at regression models in a more abstract context because they're not looking at actually using it. It's more of almost like an academic exercise. They're not looking at the consequences of making mistakes. And so in their instance, they tend to look at very simplistic measures. And it's just like getting a grade on a test. And it doesn't tell you what you got right or wrong, but it should give you an overall sense of, do you know what you're doing? I'm not sure if this measure does that. But R-square is far and away the most popular measure. And it's sort of like a correlation coefficient. It's a simple number, but it doesn't, just like a correlation didn't tell you the whole story, and R-squared doesn't tell you the whole story. It's also known as a coefficient of determination, but most people call it R-square. So what does it mean? The starting principle behind it is useful. One way of evaluating performance is, oh, you don't like my model? Okay, don't use it. What are you going to do? What's your alternative? That if you don't like the price of something, fine, don't buy it. But what are you going to do instead? Do you have another option? And that's a trickier thing, but it does reflect the reality of many instances. If you're not going to use this, what are you going to do instead? And so this may be better than nothing. Um, what is nothing in this case? What would you do if you had no model at all? You know all these customers, you've seen the data that they have balances between zero and about $2,000. But most of them tend to be on the low end. The average is around $500. So if you were to just pick a random customer and you're asked to guess what their balance would be, and you've got to pick a number, that you wouldn't pick zero, you wouldn't pick 2,000, because those are the extremes. You'd pick something in the middle. You might pick the average. Some are going to be above average and some below average, but you're picking something in the middle. In the case of ignorance, you're going to use the mean value, use the average. So on a scatter diagram, the average is 520. And for people in the middle, it's pretty much the same as the model is giving. You know, the model says for these customers over here that have a rating around 300, the model predicts a lower balance than just using 500. And for these ones whose rating is like 500 or 600, it's suggesting no, we should be predicting something much bigger. If your rating is very high, using the average is going to give you a very bad forecast because we know they're all above average out here. And if your rating is quite low, we know, well, all the customers are well below average and we should be picking a different thing. So rating does give us insights. People with low ratings are definitely below average balances. That customers with high ratings are definitely above average in terms of their balances. But how much better is using the orange line to using the black line? Well, it has to do with how bad your forecasts are. And we said that not only did we want to look at the gap between actual and forecast, but we wanted to look at the square of that difference so that we heavily penalize big mistakes and we have a small penalty for small mistakes. And so if I look at my squared mistakes with the model and I look at the squared mistakes without the model, that ratio is going to be a number between 0 and 1. I can't get it below 0 because I've got squares, and I can't, 0 would be giving perfect forecasts. I can't get bigger than 1 because I can't be worse than just using the average. So it's somewhere in that range. And if I take that ratio and subtract it from 1, we can talk about how big a reduction we've made. So there's a lot of noise present. How much of the noise have you been able to eliminate? How much of the variation have you been able to eliminate by using the model? In a sense, that's what we're doing. Many people talk about it being the variation that's explained. I'm explaining why this person has a high balance because they've got a high rating, and why this customer has a low balance because they've got a very low rating. I'm explaining why they are not average. I'm explaining why they're above average balance here and below average balance there. My explaining isn't really good for the people in the middle, but for the people at the ends, I'm quite good at it. And so we'd like to be able to explain the variation that's happening here. And that's the words that people use. My R-square is 0.75. R-square is between 0 and 100. So a lot of people like to change that to percentages because we don't like decimals. And so they'd like to say that it explains 75% of the variation in credit card balances. And that sounds really good. 75, that's a solid B performance. It's not outstanding, but it's good. For many of you, you're A students, and you wouldn't be happy with a 75 on a test. But if I told you on average, my predictions, I can explain the variation, 75% of it, you might think, hey, that's a pretty good overall performance in the model. And in fact, in practice, many people would say that is very good. 75%, that's an excellent model. Many of our models, we have an R-square of 10%, and that's not unusual. Uh, Sometimes much even lower than that. But you've got to decide, is that good enough for you or not good enough? And if you look back at this, if you were told you got a grade of 75%, and are you satisfied? Okay, I can live with that. Um, but when we look at the actual predictions, we're seeing, yeah, they're not where I want them to be. I want to be able to give much more accurate predictions than that. But when you're that percentage score is deceptive. And I find it like correlation coefficients. I find correlation coefficients are too high. I see a correlation of 0.8 and I think, that's good. And in practice, no, it's not as good as I thought it would be. Or a correlation of 0.5, hey, that's not bad. And then I look at the predictions and say, that's pretty awful. That's what we've got here. The numbers, unless you've got a mental picture to go with the numbers, they're deceptive. The number just by itself, 75%, gives you an image of really good predictions. And in fact, what you're seeing here is it's not as strong as I'd like it to be. So we've got to be careful there. And that takes us where we're going to end today, because next class, we're going to look at how to improve. So regression is, at least simple linear regression, is using one variable to predict another. That we get an equation, it's got coefficients in the equation, and it's important to understand what those coefficients are all about. But those things only reflect what's the average performance, and that formula is to describe averages. And even, a model can be really good at giving us good predictions of the average, but not very good predictions of individuals. That if you're looking at predicting averages or of individuals, both cases are value estimation problems. Okay? And make sure you understand which one is really important to you. In many cases, it's the average, actually, that's important to you. And we'll see that more in classification models. If you're interested in the coefficients, you're someone that's interested in causal modeling. What causes people to borrow more? Or what can I look at to give me insight into why people borrow more or how to increase borrowing behavior or what's important in their borrowing behavior. If I wanted to go, and we have a lot of customers that have a balance of zero or very close to zero. And if I wanted to actually identify who are those customers that don't use their card versus those that do, that's a classification problem. Regression we can use to do it, but it tends to be not very good. It's not the greatest for classification. Um, so if I use this model to give me, okay, if it predicts they're going to have a balance of less than $100, I'm going to put them into the ones that don't use their card. And if it's over 100, then they do use their card. Is that a good classification model? There may be other alternatives that are better, and there are other methods. Regression is very frequently used for value estimation, causal modeling. It does a very, very good job at it. It's the most commonly used tool for it. But they're not really good for classification models, and usually we'd use other tools for doing that. We have other strategies, and we'll introduce some of them later. Remember, though, that every model is an estimate, that we're just estimating the coefficients. They're not perfect. And it's not unusual for our estimates to be off, and it's not unusual for our predictions to be off, that we're only estimating averages. And standard error is a really nice thing for trying to look at those things. So if you're being asked how accurate are your estimates or how accurate are your predictions, find the appropriate standard error, because there are several of them. There was one for the intercept, one for the slope, there's one for the model. And so we don't know which one to use. That that and then we have that overall performance measure, the R square. And so we need to look at that as another measure of performance. So next class, I'm going to look at how to improve it. And we can improve it by adding more variables. But we can actually encounter more problems as we do that. We can also do other things. This one is a model that uses numeric variables, and it only looks at straight lines. What if the relationship is a curve? And I already alluded to that. Rating looked to be a curvy type of relationship. What if I put a curve in there? How do I do that? We have other data on our customers. Are they married? Are they male or female? Are they Caucasian? Are they students? So how do I include that type of qualitative information into a regression model? And can we do it? And it turns out we can. So there's a lot of ways I can try to improve this model. And over the next two classes, that's what we're going to do, is look at strategies for building a more complicated model that tries to capture this additional information and some of the pitfalls that may be ahead of you in doing that type of thing. And that takes us to the end. So let's call it a day today and in the class. And I will, or you'll see me again on Wednesday. If you got questions in between, please feel free to get in touch with me. You guys have a great day. It's still sunny, starting to cloud over. Lots of rain coming into tomorrow. Bye now. And in and whoops.